Yeah, in the last class we found that in buck boost and Cooke converters, there is no isolation between the input and the output. In other words, the ground or the reference point for the input as well as for the output is the same. Also, the magnitudes of the input and output cannot be greatly different. So, we can use a transformer and solve both these problems. The principle is that we should not allow the transformer to saturate. So, we discuss the operation of this circuit. We use a transformer between the input and the output. We used output also a separate voltage source, and we connected a diode in the secondary in such a way that only one winding is carrying current at a time. Okay. So, when we close the switch, current enters the dot. Current cannot leave the dot in the secondary because of this diode. Therefore, I2 is 0, primary is energized. So, we know that if the secondary current is 0, primary current is only the magnetizing current. A DC voltage is being applied to the magnetizing inductance. Therefore, the primary current, which is same as the magnetizing current, increases linearly. If the magnetizing current increases linearly, flux in the core also increases linearly. Only one winding is carrying current. There is no current in the secondary. After some time, you are opening the switch. What is the condition? Condition is that flux in the core should be continuous. If that is the case, the direction of flux produced by the secondary should be the same as that of the direction of flux produced by the primary. In other words, direction of flux produced by primary is same as the direction of flux produced by the secondary. That can happen only when, if current enters the dot in the primary, current will enter the dot in the secondary. Okay. So, in this circuit, you find when I close the switch, current Im is increasing linearly. We open the switch, current starts flowing in this direction. Okay. The so called stored energy in the inductor is transferred to this source, secondary voltage source connected to the secondary winding. Okay. What happens if I were to make a small mistake in the diode connections? In other words, both the windings were to current carry simultaneously. This is the equivalent circuit. Close the switch, current flows in this direction. So, current can also flow in the secondary. Okay. Magnetizing current was in this direction, remember. I am opening the switch. Current has to be continuous, magnetizing current has to be continuous. So, it starts flowing, it has to flow in this direction, but then there is no path. There is no path. So, diode connections are very important. If you make a mistake in the diode connections, the circuit will fail, because there is no path for the magnetizing current to flow when I open the switch. Okay. So, we found that energy from the voltage source which is connected in the primary can be transferred to another source which is connected in the secondary. Now instead of having a voltage source, you connect a capacitor and some load across it. So I have another power supply using a transformer. Okay. So this power supply is known as flyback converter. Okay. Circuit topology is same as the previous one. Only thing is I have replaced the voltage source of V2 by a parallel combination of C and R. C is equivalent to output capacitor, output which maintains a constant voltage at the output, a load is connected, a variable R. It is very popular in power supply when the power rating is less than around 200 watts or so. So if the power supply, wattage of the power supply is of the order of 200 watts, invariably you can think that it is a flyback converter. Okay, very popular in low power range. Principle of operation is same as the previous one. Okay. Current enters the dot when I close the switch. Current enters the dot when I close the switch. Current cannot leave the dot because of this diode. So primary current is only the magnetizing current, increases linearly. Voltage induced or voltage applied to the primary is VDC. The reflected voltage or voltage induced in the secondary is VDC divided by N1 multiplied by N2. So here is the equivalent circuit with dot as positive, with the dot as positive. Okay. So what is the voltage that is appearing across the diode? VDC into N2 divided by N1 with positive this terminal, anode is negative. Okay. When the diode is on, current is flowing in this direction, so definitely this terminal should be positive. Okay. So cathode potential with respect to this bus is V0. So the equivalent circuit when the diode is off is something like this: V0, anode is or the positive of the output voltage source is connected to the cathode, and this is the voltage induced in the secondary of the transformer. So voltage appearing across the diode is sum of these two. Okay. After some time, open the switch, stored energy is transferred to the secondary, direction of flux should be the same. In other words, direction of flux produced by the primary should be the same as the direction of flux produced by the secondary. So if current enters the dot in the primary, current will enter the dot in the secondary. Okay. Now what happens after some time when you want to close the switch? The I2 may not become 0. I will repeat, I2 may not become 0. So when I close the switch for the second time, whatever that current that was flowing in the secondary gets transferred to the primary, because at a time only one winding can carry the current. So in the primary I have closed the switch, circuit is complete, right, current can flow. So if current can flow in the primary, current cannot flow in the secondary. So whatever the current that was flowing in the secondary, the equivalent current starts flowing in the primary. So in other words, if there is some current flowing in the secondary, as soon as I close the switch, source has to supply a finite amount of current. Okay, similar to something in a buck converter or a buck boost converter. It doesn't happen in boost converter. Boost converter source current is almost continuous, increases and decreases. Whereas in buck converter, when I close the switch, whatever that current was flowing through the inductor, now the battery has to supply. Instantaneously, battery has to supply a finite amount of current. Same thing happened in buck boost. It doesn't happen in Cook. Okay. So if the current becomes 0 in the secondary prior to closing the switch in the primary, the source current starts from 0. So what is the significance? If the source current starts from 0, it implies that the magnetizing current is also starts from 0. So if the magnetizing current starts from 0, flux in the core also starts from 0. If there was a finite current flowing in the secondary just prior to opening the switch, when I close the switch, source has to supply the equivalent current. So the magnetizing current when I close the switch starts from a finite value. In other words, there was some flux in the core prior to closing the switch. In other words, we did not make the flux in the core 0, or we did not reset the flux. Mind you, either I am increasing the flux by increasing the magnetizing current. So when I open the switch, the current starts flowing in the secondary, flux starts decreasing. Operation is always in the first quadrant. Operation is always in the first quadrant, the BH loop. Okay. So if you see, current starts from 0 when I close the switch, okay, starts increasing, and it has become 0 prior to closing the switch for the second time. Okay. So this value of flux, residual flux, is equal to the residual flux. Magnitude should be very small, maybe nearer to the origin, this point. Okay. Instead of this, I can have some sort of this situation wherein secondary current is finite prior to closing the switch. Okay. So when I close the switch, equivalent current starts flowing from the primary, okay, and starts increasing. I'll open the switch, current starts decreasing and reaches the same point. It doesn't cut the y-axis. Mind you, this is the residual flux point. In other words, some DC flux is there in the core. So this is the variation of flux. Flux increases, it starts from a finite value. Mind you, this is at steady state. This is at steady state and decreases. Okay. See the secondary current, it has not become 0. Not become 0 prior to closing the switch. So when I close the switch here, this current forced to become 0, and immediately the equivalent primary current starts flowing from here. Equivalent starts current flowing from here. Okay. So which is the generally preferred condition? Invariably, in DC to DC converter, we operate flyback converter in discontinuous mode. Now what is discontinuous? In AC to DC line commutator converters, discontinuous conduction implies load current is discontinuous. In buck boost and choke discontinuous current implies the inductor current is discontinuous. Load current is assumed to be continuous because it's a voltage source, output is a voltage source, I am connecting a resistor across it. So voltage source implies terminal voltage is independent of the magnitude of current that is supplying. So load current is invariably is supposed to remain constant, but then the inductor current that is connected in the circuit may become 0. So that mode of operation is known as discontinuous mode of operation. Now in flyback converter or in converters wherein I use a transformer, discontinuous conduction implies flux in the core has become 0. Okay, I will repeat. In power supplies wherein there is a transformer, discontinuous conduction implies that flux in the core has become 0. Continuous conduction, it implies flux in the core is non-zero. It starts from a finite value, increases and decreases. So why am I saying that discontinuous mode of conduction is preferred? It is because we are applying a DC voltage to the transformer and operation is always in the first quadrant. We are not applying negative ampere turns to the core, okay, H is always positive. So there is some flux present in the core. Now you see here accidentally D has increased. Accidentally D has increased. It implies that most of the time switch is closed. Okay, current increases linearly. It had a finite value, current increases linearly, and most of the time accidentally D has increased, so switch is closed for most of the time. It may so happen that core may saturate. It may so happen that core will saturate. So if core saturates, either switch or the inductor or source will fail, or all three of them may fail. Okay? So we should not allow the transformer to saturate, or should not allow the core to saturate. So one of the way to avoid this situation is operate it always in the discontinuous mode. So how do I do that? Or how do I stop the core getting into saturation? Best way to introduce an air gap in between the core. In the sense, you provide an air gap in the core. So if there is an air gap, you cannot saturate it. It's always linear. Reluctance is always constant. So you can avoid this situation. But then if I provide an air gap, it implies that the coils are not tightly coupled. The moment I provide an air gap, you can have a leakage flux. So if there is a leakage flux, what happens if when I close when I open the switch? See, in this equivalent circuit, I had provided an air gap, coils are loosely coupled, there is a leakage flux now, it always comes in series leakage flux, and this is the magnetizing, or this could be considered as an ideal transformer with the magnetizing branch. Okay. Now when I open the switch, okay, there is a path for the magnetizing current. Okay, there is a path for the magnetizing current. What happens to this inductor? What happens to the energy that is stored in this leakage inductance? See, in this equivalent circuit, I will go back. See here, there is a leakage, there is a small inductance in this path here. leakage, this is the magnetizing. Okay. So when I open the switch, where can it go? This current was flowing in this direction, it has to come this way, it cannot, nor it can go this way. So you may experience or you may observe a spike because of this. Is there a solution? Yes, there is a solution. So use this sort of a branch circuit. See, I have not connected, I have not shown the secondary connections, they are still there. I have not connected, not shown the dotted polarities also, that is okay. So you have a circuit, primary circuit is something like this, 2 switches, one of the ways, 2 switches and 2 diodes. Operation is same, I close these 2 switches, current starts flowing in this direction, okay. Mind you, current was flowing in this direction, open the switch, okay. Magnetizing, that current was flowing in this direction, open the switch, now current can flow in this way. Okay. Current can flow in this way. So there is no problem about the voltage spike generated due to the leakage flux. But then there are 2 switches and 2 diodes, device losses, voltage drop across the device, all those issues should be taken into account while designing the converter. What is the transfer function now? We have not derived the transfer function for the flyback converter. What is the input output relationship? I had shown these 2 flux plots or variation of flux in the core. It starts from 0, comes back to 0 to the same point. Here also it comes with the, starts with a finite value, comes back to the same finite value. In other words, there is a steady state. It can happen only if there is a volt-second per turn balance. Okay, I will repeat. You can have a steady state or the fluxes, they follow the plot which I have shown you only if there is a volt-second per turn balance. In other words, increase in flux when the switch is on should be equal to the decrease of flux when the switch is off. Positive d phi by dt or positive d phi should be equal to the negative d phi. Volt second per turn. What is that? See here, volt VDC into dt is time, volt second per turn. Per turn. It is nothing but increase in flux. Increase in flux. Okay. So increase in flux is this is the source voltage is the one which forcing the flux in the core. VDC divided by N1 into time for which the switch is closed dt should be equal to the decrease in flux. Now decrease in flux is V0 is the voltage applied to the secondary V0 to number of turns in the secondary is N2, and this is the time for which the secondary is carrying current, assuming it is in continuous conduction or at the boundary, remember 1 minus dt. So I will equate it, increase in flux should be equal to decrease in flux. I will find that V0 is equal to VDC multiplied by N2 divided by N1, the turns ratio, divided by D into 1 minus D. So D divided by 1 minus D, this is nothing but a buck boost converter. Transfer function for buck boost, D divided by 1 minus D. But in addition to this term, there is N2 divided by N1, the turns ratio. So, hence the name isolated buck boost. Okay. It is also isolated buck boost. There is the isolation, the transfer function is same as the buck boost converter. Okay. Now, in this transfer function you can see that V0 and VDC can be greatly different. V0 and VDC can be greatly different because I will fix or I will choose this ratio, suitable ratio. Okay. By suitably selecting this ratio, magnitudes of V0 and VDC can be anything now, they can be greatly different. So, invariably D is maximum value of D to be approximately chosen to be 0.5. We do not choose, or designer does not take the worst condition to be 0.5, it takes this to be 0.5, okay, and choose this N2 by N1 suitably. Which is another important parameter in flyback transformer design. Mind you, though it may be a transformer, only one winding is carrying current, only one winding is current. Another important parameter is the primary inductance L1. Why? We will see here. What is the peak value of the current when the switch is closed? It is IP is equal to VDC divided by L1 into D into T. The slope of this line is VDC divided by L1, okay, and time for which the switch is closed. So, what is the input power? Input power is input voltage VDC into the average value of the primary current. What is the average value of I1? It is nothing but half of IP, the peak value, into dt divided by t. Okay. It is area of this triangle divided by the time period, divided by the time period. Area of this triangle is half IP, this is dt divided by the time period. So, this is the average power input. Now, if I neglect the losses, this is equal to the output power. So, if I know the output power and if I know the input voltage, I can calculate the peak value of current IP. Okay. Now, if I know IP, I can choose a suitable value of L1. Okay. So, primary inductance is a very important parameter in the transformer design. What are the other advantages of flyback converter? Why it is so popular? It is nothing but an isolated buck boost. Apart from the isolation between the input and output, I told that the magnitudes of VDC and VO can be greatly different. Another important advantage is that you can have multiple outputs. See, in buck boost or choke, there is one input and one output. Whereas here you can have large number of outputs, one input and large number of secondaries. So, when I close the switch, energy is stored in the primary no current is flowing in the secondary because of these diodes. Open the switch, energy is transferred to these secondaries. So I can have large number of secondaries now. Now I can have positive voltage and I can have a negative voltage, I can have any number of voltage. So plus 5, minus 12, plus minus 5, so on, anything. See, here are the various configurations. Current leaves the dot, current leaves the dot. Okay. See here, current enters the dot, current enters the dot, current enters the dot, current leaves the dot. So this is positive. Okay. Now see here, current is entering the dot here. Here also current should enter the dot. See the circuit connections here. So this is positive, this terminal is positive, this terminal is positive. So here this is positive, this is negative. So similarly here, current enters the dot, current enters the dot. See the diode connections now, I have interchanged. I have connected a diode here. Now this is positive, this is positive, this is negative. Now this can be a reference point, reference point. Okay. So you can have multiple outputs, multiple outputs. So point to be remembered in flyback is that diode connections are very important. You should connect diode in the secondary in such a way that only one winding is carrying current at a time. Okay. I told you that flyback converter is very popular in low power range. Why? What is the principle of operation? We use a transformer, but then we operated like an inductor, in the sense only one winding is carrying current at a time. Suppose someone says, I have used a transformer, I expect that both the windings carry current simultaneously. I transform the energy from primary to secondary. But then we did use a transformer in a flyback converter, but then we connected a diode in the secondary such a way that only one winding is carrying current. We have seen in AC circuit operation, secondary current may be 0, primary is just supplying the magnetizing current. But we never had a situation wherein primary is open and secondary is carrying a current. At least I never encountered that sort of a situation in AC circuit analysis. But here secondary is carrying current when there is no current in the primary. So in other words, I am storing the energy in the magnetizing inductor and transferring it to the output. The primary current is only the magnetizing current. Remember, primary current is only the magnetizing current. I2 is 0 when I1 is finite. When there is current in the primary, there is no current in the secondary. So therefore I1 is always equal to Im. It's the magnetizing current that I am storing, I am transferring it to the secondary. So let's see what happens, or what happens when I increase the power rating, or if I want a higher output, what sort of a topology do I need to use? So there is one more converter, what is known as a forward converter, forward converter. See the circuit connections. Again I use a transformer, 2 winding transformer, okay. Again let me make few assumptions. I am assuming that transformer is ideal, okay. In other words, mu r is infinity, therefore reluctance of the core is 0. So ampere turns required to establish the flux in the core is 0. In other words, magnetizing current is 0. Remember, I will repeat, mu r is infinity, therefore magnetizing current is 0. See the circuit topology. Okay. Close the switch. Current enters the dot. Current enters the dot. Correct direction for the secondary current is to leave the dot. When primary is carrying current, the correct direction in the secondary is to leave the dot. Current can leave the dot. See the diode here. Current can leave the dot. So path is something like this. Diode, inductor, output, capacitor and load back to the secondary winding. Okay. So therefore, what is the primary current? It is the equivalent secondary current. I1 is equal to I2 prime, because Im is 0, no magnetizing current, no magnetizing current. What is the voltage that is applied to the primary winding? It is VDC. What is the voltage induced in the secondary? It is VDC divided by N1 multiplied by N2. Okay. Dot is positive, connected to the positive of the battery. So this is also positive. Okay. So the equivalent circuit you see here, positive, diode is conducting, inductor, output stage back here. DF is off. See in this circuit, diode DF is off because this is positive, this is also positive, this is negative, a reverse voltage appeared across the diode. So diode DF is off. So when the switch is on, the equivalent circuit, the secondary, it looks something like this. Don't you think it's a very familiar circuit? This is nothing but a buck converter with the input voltage VDC is replaced by VDC into N2 divided by N1. Here the forcing function is voltage induced in the secondary, whereas in a buck converter voltage forcing function is the input voltage source itself, VDC itself. Here the forcing function is VDC into N2 divided by N1. Okay. What happens when I open the switch? What is the current just prior to closing the opening the switch in the primary? There is no magnetizing current, because we have assumed a core to be ideal, or mu r is infinity, reluctance is 0, magnetizing current is 0. So primary current is equal to the secondary current, I1 is equal to I2 prime. So when I open the switch, I1 becomes 0. Okay. There is no magnetizing current. The question of providing a path for the magnetizing current does not exist. Okay. So what happens to the current in the secondary? Okay. Now, the moment I open the switch in the primary, there is no current in the primary, therefore I2 is also becomes 0. Okay, this current becomes 0. This current or the output filter current should be continuous. It was flowing in this direction, starts flowing this way, df. See in this circuit, when this current becomes 0, this also will become 0. Okay. If this becomes 0, this may not be 0. Let me tell you one thing, this is inductor current. Output is a current source type similar to buck or Cooke converter. I can represent this as a current source. This current may remain approximately constant. Okay. So when I close the switch, I2 that is equal to IL increases. Okay. Why it is increases? See here, a voltage, a DC voltage is being applied here. So I2 increases slightly depending upon L and dt. Okay. Voltage appearing across the inductor is VDC into N2 divided by N1 minus V0. Okay. So when I open the switch, DF starts conducting, voltage appearing across the inductor L is nothing but V0 itself. Okay. So the transfer function is V0 is equal to VDC N2 divided by N1 into D. Okay. When the switch is opened, voltage across the inductor is V0 for this duration, 1 minus D into T duration. So this is nothing but isolated buck converter. Isolation because there is a turns ratio. If this is 1, this is nothing but V0 is equal to VDC into D. Okay. So forward converter is also known as the isolated buck converter. Okay. What happens if I consider a non-ideal transformer? Let me tell you one thing, you cannot have an ideal transformer. Mu r is finite, not equal to infinity. R is finite. If R is finite, ampere turns required to establish the flux in the core is again finite, is not 0. Source has to supply some ampere turns to establish the flux in the core. Okay. So when I close the switch, if there is a finite current flowing in the secondary, so what is the primary current? It is equivalent secondary current plus the magnetizing current, So see a non-ideal forward converter using a non-ideal transformer, or this is a practical forward converter. Mind you, let me tell you, the previous forward converter cannot exist. You cannot have a forward converter with 2-winding transformer. This cannot exist. Because you have to, source has to supply some ampere turns to establish the flux in the core, and that current has to be continuous. See, this inductor current is continuous because DF provides a path. It was flowing, when I close the switch, I2 starts flowing, that is nothing but IL, DF was off. So this is the path. When I open the switch, D2 turns off. So this current can flow through this diode. Okay. There is a path for the load current or inductor current. Okay. Since there is no leakage inductance here, there is no magnetizing current here, circuit works satisfactorily. A circuit can work, but there is always a finite magnetizing inductance. ampere turns required to establish the flux in the core is finite. Okay, that has to be continuous. So when I open the switch, there is no path for the current to flow. So this is a practical forward converter. There are 3 windings. This is nothing but the previous circuit. Okay. So I have used yet another winding, a tertiary winding, okay, with the diode, and see the dotted terminal. Okay. And the third branch is connected to the same supply as of now. Let us see what we can do with this sometime later. Okay. How does this work? I told you, you have to provide a separate path for the magnetizing current. So how does this circuit work? Close S. Okay. Magnetizing current or flux in the core increases linearly, similar to the flyback, okay. But then there is no secondary current, but in forward converter, when I close the switch, there is an equivalent current flowing in the secondary. Secondary current can flow because of the diode connection. I2 is finite, so there is I2 prime, the primary. So voltage applied to the magnetizing inductance is VDC. So Im increases linearly with time. Okay. What is the voltage induced in N2 turns? It is VDC multiplied by N2 divided by N1. What happens in the tertiary? Or what will happen in this circuit? This is the one which is producing the flux, okay. Current enters the dot, so right direction here is to leave the dot. You cannot have that situation because of D3. Current cannot leave the dot, okay. Current can only enter the dot. Dot is positive, dot is positive, dot is positive, dot is connected to the positive of the battery, positive to cathode, anode is grounded, D3 is reverse biased, no current can flow in this direction, or in other words, no current can leave the dot in the tertiary winding. Similar to a flyback connection. Only difference is flyback we have connected a capacitor and a resistor, whereas here I am connecting it to the same source. Okay. So what is the voltage induced in this winding? Voltage applied to the primary is VDC. So voltage induced in the tertiary winding with N3 is VDC into N3 divided by N1. Okay. VDC divided by N1 multiplied by N3 is the voltage induced in the tertiary winding. Okay, let me go back. So this is a circuit connection, see, with the dot as the positive, VDC into N3 divided by N1. Other end of the transformer winding is connected to positive of the battery, VDC. So this is the circuit connection. What is the voltage appearing across D3? Series connection of these two voltage sources. So voltage appearing across D3 is given by this equation. Okay. What is the voltage appearing across the freewheeling diode in the secondary? It is the secondary induced voltage VDC into N2 divided by N1. You open the switch after some time, what will happen? Go back to the previous circuit, open the switch, I1 becomes 0, so I2 also will become 0. But then magnetizing current has to be continuous. IL, load current here, is continuous, there is a path. There is a path here. Now D3 starts carrying the current. See, this D3 and N1 or this is nothing but a flyback converter connections. Flyback converter connections. Okay, flyback converter connections. Now, how do I explain? See, when I open the switch, I said flux try to decrease, d phi by dt is going to be negative. So, in other words, all dotted, this terminal is going to be negative. Okay. If this is negative, this is positive. This is negative, anode is connected to ground. So, D3 can conduct, D3 can conduct, current can flow through this path back to source. Okay, back to source. Okay, D3 starts conducting. But current that is flowing through D3 or the current that is flowing through that N3 winding is only the equivalent magnetizing current. Let me tell you one thing, it is just equivalent magnetizing current. So, what is the peak value of the magnetizing current just prior to opening the switch? It is VDC, the voltage applied to the primary turns or N1 turns, divided by Lm is the magnetizing inductance, multiplied by the time for which the switch is on, dt. Now, that current gets reflected to the tertiary winding or winding which is having N3 turns. So, the peak value of current that is flowing in N3 is given by Im into N1. Im is the peak current that was flowing in the primary winding, just peak value of the magnetizing current, just prior to opening the switch, that was flowing in N1 number of turns. Now, this current gets reflected in the tertiary which is having N3 turns. What is the voltage applied to N3? It is VDC with dot as negative, because other end of the winding is connected to the positive. So, this is connected to positive. So, this has to be negative. In other words, this is negative, this is negative, this is negative. Okay. Dot as negative. So, to sum up the operation is closed switch S, current enters the dot, current can leave the dot. Okay. The equivalent voltage is applied here, IL increases linearly. In the tertiary winding, current is 0 because current cannot leave the dot. Open the switch. Okay. Magnetizing current has to be continuous, that it starts flowing in tertiary winding. All dots are negative now. So, I2 is 0, I1 is 0, I3 is finite, it provides a path for the magnetizing current. Okay. So that's about the forward converter operation. More about it we will see in our next class. Thank you.